Hello, guys. So today we're gonna be covering the second half of chapter number 5, Alcohols and Alkyl Halides, Introduction to Reaction Mechanism. And for today, we're gonna cover basically the reaction of alcohols with hydrogen halides for unimolecular nucleophilic substitution mechanism or SN1 mechanism. Also, we're going to talk a little bit about the structure, bonding, and stability of a species that is known as the carbocations, the effect of alcohol structure in reaction rate, specifically for this alkyl halide type of reaction, stereochemistry, and the SN1 mechanism. We're going to talk a little bit about carbocations rearrangement and also the reaction of methyl and primary alcohols with hydrogen halides. Then we're going to talk a little bit about other ways that we can create those alkyl halides other than basically with hydrogen, um, um, hydrogen, I forgot the word, halides, hydrogen halides. And finally, we're going to talk about sulfonate as alkyl halide surrogates in that case. So, um, the last time I showed you this overall reaction of terbutyl alcohol and hydrochloric acid or hydrogen chloride. And the product of this reaction is terbutyl chloride plus water. And I mentioned that the first reaction here was the acid-base reaction. The acid-base reaction is the fastest reaction that we're gonna see. So because we have the presence of an acid as HCl, and we have an alcohol that could behave as a base, those electrons from oxygen are going to attack the hydrogen of the hydrogen halide, and then those electrons that are here between hydrogen and chloride is going to go to the chloride. Remember, hydrogen can create just one bond. So because the oxygen is creating one bond between the oxygen and the hydrogen, they need to get rid of this bond. So those two electrons are going to go toward the chlorine. That's why you see that complete arrow going, taking those two electrons toward the chlorine. And then we're going to have this part of the molecule that is water, okay? And also we have the chloride ion. And that's going to be the first step of the mechanism, which is the protonation. The second step is the dissociation. And here, remember that the word dissociation means that when we separate in ions, okay? So we're going to create ions in this step. So what is happening here is that this molecule in here is water. The water is gonna leave. That's what is called a leaving group. Okay, so it's a leaving group, an excellent leaving group, because when it leaves, it produces a molecule that is completely stable as water. Okay. However, because those two electrons from between the carbon and the oxygen are getting to the oxygen due to the deficiency, the lack of electrons in oxygen, now this carbon is gonna have that deficiency in electrons, and it's going to create a positive charge in that carbon, and that is known as carbocation. Okay, that's a carbocation. So we have the carbocation and we have the molecule of water. We create an ion, so that's why this second step is known as dissociation. Okay, and the third step is going to be the association. That is the opposite. Now we're going to have this species here that has a negative charge, it has an excess, it's a big electron density, okay? And this is going to behave as a nucleophile, which is going to attack the electrophile. The electrophile is the species that lack of electron density, and that's going to be the carbocation. And then this chloride ion, which has a lot of electrons there, is going to act as a nucleophile, and the nucleophile always is going to attack the electrophile. And by doing that, it's going to create a new bond between chloride and the carbocation, and that's going to be my product, the terbutyl chloride. So this is the mechanism, the step-by-step process to explain how the terbutyl alcohol in the presence of hydrogen chloride can produce a terbutyl chloride and the water. Okay, so now let's go step by step and in more detail in each of those steps. So the first one is a proton transfer. As I mentioned before, is the acid-base reaction where you're going to basically create the electrophile in that sense. So HCl is going to donate a proton to the basic oxygen atom of the alcohol. So the alcohol is going to behave as a base and the HCl was obviously as an acid. And by doing that, we're going to protonate this OH, okay, and we're going to produce this part of the molecule, which is an anion, but it's a molecule of water, okay? It's a molecule basically of water in here. So this oxygen, because it has three bonds and two electrons, has a charge of positive one. Because of that, those electrons between the oxygen and the carbon are going to get close to the oxygen. And this carbon is going to be a little bit more partial positive, okay? And we have also the chloride ion, which is the product of the deprotonation of the acid. This is the acid, so it's the conjugated base. This has a higher density of electrons. This one also has a lower density of electron, but it's attached to those pairs of electrons that eventually is going to stabilize, okay? So this first step was the acid base step. The pKa values confirm that this is a highly favorable process because it's an acid-base reaction. And now, as I mentioned before, this carbon is going to have a little bit more positive charge in here than in here. The second step is the dissociation. Now that we have this species in here, this H2O is an excellent living group. Okay, so when I said a living group is that this group is going to leave that molecule. And by doing that, it's going to take these two electrons, okay, in a way to create those two lone pair of electrons and create the stable molecule of water. But at the same time, it's going to leave this carbon without those two electrons, and it's going to create a positive charge, which is the carbocation, okay? And this is the dissociation, okay? So once again, this is a good living group. It's going to be released, okay, by itself with those two electrons to stabilize this charge and create water, which is a pretty stable molecule. And then it's going to create a carbocation in here, which is a positive carbon. And this is a little bit unstable. Okay, so that's why when we see here the progress of the reaction, we see here that when we protonated the alcohol has this energy. And when we create the carbocation, is this one has a higher energy than this one. It's more unstable because it's a species with a positive charge. And also, it's important to point out that between these two molecules, these intermediates, we have this complex in here that is known as the transition state. The transition state always going to be in the top of this crest, okay? And it represent something between those two intermediates. It's going to show us the bonds that have been broken and the bonds that are going to be created, okay? So you use those kind of dash lines to show which bonds were broken and which bonds are going to be created depending on the situation, okay? But this is the transition state. It's going to be that kind of complex that is going to show us what was broken and was going to be created if that was the case. In this case, we're broken in this, or this bond was broke, so that's why we're showing this here, okay? It's between the oxygen and the carbon in dash lines. This step is slow due to the formation of a relative unstable carbocation. Also, you can see here that to go from here to here, we need to go over this activation energy, which is pretty high. So that's why this step is the slower step in this reaction, okay? Is the slowest step in that reaction due to that high amount of activation of energy. The positive carbon that we create here in the carbocation is now the electrophile, okay? And the chloride ion, which has a lot of electron density, is going to be the nucleophile. And as I mentioned before, organic chemistry is when a nucleophile attacks the electrophile. Our next step is the association, where we basically do that step of the nucleophile attacking the electrophile. So the chloride ion associate with the carbocation to form the carbon chloride or chlorine bond. So here we have the carbocation, here we have the chloride ion. This nucleophile is going to attack that electrophile. It's going to be pretty fast. The activation energy is pretty low in there. And we're going to have our product. And as you may see here, the product is pretty stable. So that's why it basically drop until this point. And that activation energy is so small that it's going to be pretty fast. That third step of the association. In here, we can see also that transition state, okay, which is going to represent what bond is forming between the carbon and the chloride ion. This step forms the product and is highly favorable and rapid, it's fast. And here we have the big picture of all the three steps. The first step was the production of the electrophile, in this case, the protonate in that living group. So here we have the transition state, okay, of that process. We are breaking the HCl bond and we are creating the OH bond. So that's why we have this in here, okay? And then this is going to be dissociated to create a carbocation. This is going to be my rate limiting step. It's going to have the higher activate energy of activation in this reaction. And then we have the transition state between these two species. Then we have the carbocation that is electrophile, and the nucleophile of the chloride is going to attack that electrophile to eventually create my product. And this is also the transition state, which represent which bond is producing between the chlorine and the chloride and the carbocation. And also it's a pretty fast kind of reaction that energy of activation is small as compared with this one in here. Now, let's talk a little bit about the carbocation now that we introduce you to this new species. The carbocation, they're really, really important. We're going to see them a lot in a lot of different reactions that we're going to be learning in this year. So, the stability trends of carbocations are stabilized by attached alkyl groups. Okay, so we're going to have a carbon that has a positive charge. Normally, we have hydrogens around it, but also we can have R groups or alkyl groups. Those alkyl groups can be methyl, ethyl, propyl, any carbon hydrogens type of substituent. Okay, so as long as you have a lot of them, they're going to stabilize better that carbocation. So in that sense, you may expect that a tertiary carbocation is going to be more stable than secondary, more stable than a primary type of carbocation. The methyl carbocation, which is just a carbon with three hydrogens, and primary carbocations are off limits. That means that they are pretty unstable. They're basically don't exist. Okay, they're pretty unstable. Alkyl groups are electron donating. The alkyl groups are electron donating. That's why they can stabilize that positive charge because through that sigma bond between those carbons, they can provide a little bit of electron density, stabilizing that positive charge of the carbocation. Here we're going to have a representation of the stability of each of the carbocation. We have the methyl cation in here, just carbon with three hydrogens, the positive charge. Then we have the ethyl cation, which is basically a primary carbocation with a methyl group in here. This is the least stable of all the carbocations. And then we're going to have the isopropyl cation, which is a secondary cation, carbocation. It has two methyl groups and a hydrogen. So it's a secondary carbocation. And then we have the terbutyl cation, which is a carbocation with three alkyl groups or three methyl groups. Remember, this can be methyl, it can be ethyl, any kind of carbon hydrogen compounds or R groups, okay? It's not necessarily just methyl. This is just for convenience to make the molecules small, so but you need to count all the carbons around that carbocation, and that's going to give you an idea if it's primary, secondary, or tertiary carbocation. And that stability is going to increase with the number of alkyl substituents. Also, another thing that can stabilize those carbocations is the resonance delocalization. We're going to see that a little bit later, but they are really, really important factor that could stabilize these carbocations. So the electron, we're going to see here now a representation of how those alkyl groups decrease that or disperse that positive charge. So here we have the methyl cation. As you can see here, everything is positive. There's no kind of negative or electrodonating part in that carbocation. In here, we have the carbocation, but this methyl group somehow decrease or disperse that positive charge. When we have two, that dispersion is bigger, and when we have three methyl group, basically you don't see that positive charge is pretty stabilized by those methyl groups or alkyl groups around the carbocation. So one of the explanation for this behavior is in a non-traditional form, resonance form, also show that this hyperconjugation effect. So it's basically the hyperconjugation that stabilize those carbocations through those alkyl groups. And how does this happen? Basically, is that we have here a carbocation with a alkyl group that has hydrogens. Basically, we remove this hydrogen from here, and these two electrons can create a double bond between those carbons, and that's going to be how they stabilize that positive charge. This is an equilibrium that goes pretty fast. Okay, so it goes for backward and forward, but at the same time, it's going to be doing this with other carbons around it, and that's how basically stabilize that carbocation. As much as you have more than that, as long as you have more of that, it's going to make those equilibrium more frequently, and that's going to stabilize that positive charge of the carbocation. And that this is known as hyperconjugation. So the way that those alkyl groups stabilize that carbocation is through hyperconjugation, which is this process, okay? When they create that type of double bond and it's in equilibrium, so they go backward and forward, backward and forward. So when applying hyperconjugation to carbocations more complicated than the ethyl carbocation, it is helpful to keep track of various bonds. So in a way to make it more simpler, we're going to use the Greek letters. So beginning with the positive charged carbon and label the three bonds originating from it with the Greek letter alpha. So the carbocation and the three bonds that are attached to that carbocations are known as alpha. Proceed along the chain, labeling the bonds extending from the next carbon beta and from the next carbon gamma, and so on. So we're going to have here the alpha carbon, okay, with the three bonds, beta carbon, and the gamma carbon. So that's how basically we're going to label them in a way to identify those type of interaction between them in hyperconjugation. Also, we're gonna learn how the structure of the alcohol can affect the reaction rate. Okay, so we have learned about the carbocation that basically the more stable that we have is gonna be basically faster in that sense. So now, what about the structure of the alcohol? Hammond postulates that the transition state resembles the species to which it's closest in energy. So I told you before that between the two intermediates, we're going to have this peak, this crest, and this crest always we're going to have a transition state, which is going to represent those bonds that are forming and those bonds that has been broken. Okay, so if you have if the previous step you just break bonds, you're going to show those one. If you're going to create bonds, you're going to show those one as well. Okay, so and you're going to use those dash lines in a way to represent which one was broken and which one's going to create. Okay, be created. So, and this is going to be closest, okay, resembles the closest intermediate to it. So it's going to be more like this than like this. So that's why the separation between them is larger in here than in here. If this were closer to here, this two will be more close, okay? But because it's closer to the second intermediate, means that basically they are separate completely, but they still have the bond that was broken in there, okay? So that's why this that transition state is called the transition state in this step. In the slow step of this unimolecular nucleophilic substitution, the rate-determined transition state resembled the carbocation. So this is going to be similar to the carbocation. As you can see here, this is pretty far away, and you can have here just the carbocation as you have it in here. Structural factor that stabilize the carbocation will also stabilize the transition state and make the reaction faster. Okay, so whatever stabilize this also is going to stabilize this, and that's going to make the transition, that reaction quick faster. More stable carbocations more rapidly than less stable carbocations. So if the carbocation is more stable, the reaction is going to be fastest. If the reaction is less stable, the reaction is going to be slower. Okay, so we're going to show that in the next slide in here. We can see this one is for the methyl carbocation, and you can see the higher activation energy, which is going to make this pretty slow. Okay. The secondary, or sorry, the primary carbocation that comes from this alcohol is going to create a species that is a little bit more stable than this one, and that's why the activation energy is lower. So this one is going to be faster than the methyl carbocation. And also the secondary one in here is going to have the lower activation energy as this one because this carbocation is more stable. So that's why this one is going to be faster. And the tertiary is going to have the lowest activation energy of all. And because the tertiary carbocation is more stable than any of those carbocation, and that's why the reaction is going to go faster. Okay, so this is the fastest reaction. Whenever you have a tertiary alcohol, is going to be the faster reaction. Whenever you have a primary or methyl type of alcohol, it's going to be pretty slow. Okay, so that's how the structure is related with the reaction rate. As more stable because of the substitution, you're going to have a faster reaction. As less stable because you have less substitution, you're going to be the slowest. Now let's talk about the stereochemistry and the unimolecular substitution, nucleophilic substitution mechanism, okay, the SN1 mechanism. And let's talk about the stereochemistry. So in this case, when we have the secondary alcohol, we're going to have something that is known as inversion configuration. The inversion configuration, as we know, we have two type of configuration, R or S. So in the inversion configuration, your reactant is going to be R, but your product is going to be S. Is the invert, okay? Or if you start with the S, your product is going to be R. Okay, so that's what is known as the inversion of configuration. So the stereochemistry goes from R to S or from S to R because remember now you're going to substitute one alcohol with another molecule or atom, and that's going to change also the configuration of your product. And how does it happen? Let's see. So here we have the OH, the alcohol. This one is an excess enantiomeric. We have 84% of S and 60% of R. And when it reacts with HCl to produce the alkyl halide, we have 70% of R and 30% of S. Okay. It was expected to have 84 of R and 16 of S. However, we have a little bit less. Okay, as we can observe there. Note that some retention of configuration, that is known as retention of configuration, is when you keep the same configuration. If you start with R and finish with R, that's retention of configuration. If you start with R and finish with S, that's going to be the inversion of configuration. Okay. And this retention of configuration does occur due to the attack on the same phase as the departing leaving group. And we're going to go over that in a few seconds. The unstable carbocation remains close to the leaving group, blocking one phase of the carbocation. So here we have the first step, which was the protonation of the alcohol, okay? And then, as we know, this is a good leaving group. It's gonna release, and we're gonna have produce a carbocation in here. Now, something that I haven't mentioned before is that the hybridization of the carbocation is sp2. If it's sp2, the geometric form of that carbocation is gonna be what? Trigonal planar. Okay, so it's going to be a plane. It's going to be flat. So if it's going to be flat and we have the carbocation, the nucleophile can attack from this side or also can attack from the other side because it's flat. It has 50% of probability to attack each side. Okay. However, what is happening here? In here, we have, when this is leaving, we have a secondary carbocation, which is not that stable. Okay. So that's why this water is not going to go so far away. Okay. It's going to stay close to the carbocation to try to keep it stabilized. Because of that, that water is blocking that phase of the for the chloride or the nucleophile. Okay, and in that sense, the nucleophile is going to is going to attack more easily the bottom phase instead of the upper phase. So that's why this one is going to create that inversion. Okay, you can see here that now that the chlorine is the bottom, the oxygen was in the top, the alcohol first. So now the chlorine is in the bottom. So that's why you have the inversion of configuration. Okay. But some of them are going to be able to basically attack in the same phase as the living group, and those are going to be the retention one. So you started with 84 and finished with 30, but you expect 16 of the S, but you have a little bit more because some of them were able to attack that same phase of where the of where the water was living, okay? But most of the time when it's a secondary, you're going to have more of that inverse of configuration than the retention of configuration, okay? Now, scrambling. Scrambling is a situation that we're going to see when we have tertiary carbocations, okay? That comes from tertiary alcohols for now, okay? So, chiral tertiary alcohols react to give a racemic mixture of tertiary alkyl halides. So, a tertiary alcohol, maybe one enantiomer, you have the R, but when it react with the hydrogen halide, it's going to give you a racemic mixture. It's going to give you 50% of R and 50% of S. And why is this? Why with tertiary can give me a racemic mixture, but secondary always you're going to have more an excess, an enantiomeric excess because it's going to attack more one side than the other one. And this is because the tertiary carbocation is pretty stable. Okay, the tertiary carbocation is really stable. So when that molecule of water is released, it's not going to stay close in a way to stabilize that carbocation because it's pretty stable. So because it's get far away, now the nucleophile can attack, has free way to go in both sides. Okay, and that's why we have a 50-50%. So here we have an alcohol, okay, a tertiary alcohol. We use here HBr. So now we're going to add the Br is going to substitute the OH. The first step is going to be to create water. Okay. The water is a good living group, is going to be released, and we're going to produce here the tertiary carbocation. That tertiary carbocation, as we mentioned before, is hybridized sp2. So it's going to be trigonal planar. Okay. So the bromide here is going to have the option to attack both side of that face. Okay. Both faces. So can attack from the front or attack to the back. And by doing that, it's going to be 50-50%. So that's why we have the racemic mixture. Okay. This is not going to be any more optically active as was this one. Okay. Because it basically have 50% of the R and 50% of the S. And that's what is known as scrambling. So the configuration at the original stereocenter is scrambled. Okay, it just went from one specific enantiomer to a racemic mixture. You have a scramble of stereocenters now, or configurations. What happened when we have an equivalent phases? So chiral tertiary alcohols react to give an unequal mixture of diastereomic alkyl halide. Okay, and this happened because we have a molecule that has two unequivalent phases. They are not the same in each side. So we have this part in here and this part in here. In this top face, we have the terbutyl that is basically in an equatorial position pointing up. But in the bottom, basically, we don't have any of those substituents. Okay, so that's why we have that situation where we have two different phases, and that's going to create two diastereomers. Okay, so we're going to have an attack from this side of the molecule, and we're going to have an attack from this side of the molecule, and these are going to be my two products. This one is my methyl cis compared to the terbutyl. Okay, it's going to be 18 to 22%, and methyl trans to the terbutyl is going to be 80%. So these are going to be my two diastereomers, okay, that we're going to produce from this one that is basically has an equal distribution of the phases. So here, two phases diastereomic alcohols give the same distribution of products. So in this case, they are diastereomers, but if we use this one and we make the two possible products, let's say it's going to be 40 and 60, this one also is going to give me 40 and 60, okay? Because of the same thing. When we remember when we release this molecule of water, eventually we're going to have a flat compound in here, a flat carbocation. When this molecule is going to be protonated and release the water, we're going to have a flat carbocation. These two are going to be the same. So that's why the products are going to be the same, even though they came from two different diastereomers. Okay. Now let's talk about something really, really, really interesting that we're going to be talking a little bit also during the next couple of chapters is the carbocations rearrangements, carbocation rearrangements. Sometimes we're going to have unexpected products, and one of the possibility is the rearrangement of carbocations, of why we have an unexpected product. In some reaction of alcohol with the hydrogen halides, unexpected products are obtained. So for example, here we have 3,3-dimethyl 2-butanol. The expected product is going to be what? So we're expecting this OH to be substituted by what? By this chlorine. Okay, so this chlorine we expect it to be attaching here. So we have a methyl 2 chloride, 2,2-dimethyl butane. Okay, butane, yeah. But we have 2-chloro 2,3-dimethyl butane. So we can see here that something happened here. Okay, we have basically a rearrange, okay, of the molecule. And here we have now two methyl groups, while before we have one methyl group and one hydroxide. And in here, this carbon has three methyl groups, and now this carbon has just two methyl groups. So something happened, okay? And basically what happened is known as a shift methylation or methylation of shift methylation, okay? So we move one of these methyl groups to this carbon, and then the chlorine or chloride attack this carbocation in here, and that's the product of this reaction. We're going to go over that in a few seconds, but that's a big picture, okay? There was a rearrangement in where this methyl group shifted from this carbon to this carbon. So the carbon skeleton appears to have rearranged, and the chlorine ends up at an unexpected site. In particular, a CH3 group appear to have migrated. So here is the methyl group that migrated to this carbon. And this shift could be also of hydrogens. So we can move hydrogens or methyl groups to basically create a more stable carbocation. So these are two important things that you always need to keep in mind whenever you're going to do rearrangement of carbocation. Number one, involves movement by only one carbon. So if you're in carbon number one, you can move to carbon number two. That's the only step or that you can do. Okay, the only movement is from one to two, from one to two, from one to two. It could be three and four, but it's going to be just the two carbon needs to be neighbors. Okay, adjacent by each of them. And number two, and more important, that migration should lead to a more stable carbocation. That's really, really important. You're not gonna make a rearrangement to go from a secondary carbocation to a secondary carbocation because you're investing a lot of energy to make this. However, if you go from a secondary to a tertiary, now you're creating a more stable carbocation, you're releasing more energy, and even though you invest a little bit of energy at the beginning, but that losing of energy to create a more stable carbocation is going to make it worth it. Okay. So in that sense, you need to always create a more stable carbocation in a way to move a hydrogen or a methyl group in that sense. Okay. So those are the two things that you always need to keep in mind. The movement is between two carbons, close carbon, and needs to create a more stable carbocation. So for example, this is carbon one and this is carbon two. You move this methyl group to this carbon, okay? We're not talking here about the nomenclature number, okay? It's just carbon one and two. So they're basically together. So that's why you can move this methyl group to this carbocation. To make this movement, you go through an intermediate or a transition state. Okay, that transition state, as we mentioned before, represent the broken bond and the new bond. So here we broke this bond between this methyl group and this carbon and create a new bond between this carbon and the CH3 and this carbon. So that's why you have this dashed lines in here, creating that transition state. And eventually, we're going to move those two electrons to create this new bond. And that's why you move this or you create this positive charge in this carbon number one. So you went from a carbocation, what type? Secondary, you have one carbon in here and one carbon in here, secondary carbocation to create a 1, 2, 3 tertiary carbocation. Okay, so that's why this methyl shift is allowed. Okay, it's allowed. So this is a new electrophilic carbon, okay? And that's why the chloride can attack now in that carbon. And that's the explanation of why we have this unexpected product, okay? This methyl shift converts a secondary cation into a tertiary cation. And that's the reaction that we had before, okay? And that's the explanation of why we, instead of substituting this one in here, we have it in here. This is basically an energy diagram that explained, okay, that methyl shift. So here we have the carbocation, we have the p orbital, empty p orbital. We have here the methyl group, hydrogen and carbon. So we have the secondary carbocation. In here we have that transition state, okay, on top of that crest that shows the bond that is created and the bond that it was broken. So, and now we're going to break this bond in here and create this p empty, okay? And then we're going to have those electrons in this carbon in here with the CH3, and we have here the CH3 that was migrated from this carbon to this carbon, and now we have the carbocation in this one, and we have the one, two, three tertiary carbocation. That's why this is more stable than this one, okay? And even though we invest a little bit of energy, but we want this all stabilization by investing this amount of energy. So remember, you always go from a less stable carbocation to a more stable carbocation, never from a more stable carbocation to a similar energy carbocation in energy. Okay, so never go from secondary to secondary or tertiary to secondary. It's always secondary to tertiary. Okay, more stable carbocation. Also, we can have the hydride shift. It's called hydride because in this case, we're attacking this positive charge, which is an electrophile, with a nucleophile. So this hydrogen should have two electrons, okay? And those two electrons are the electrons that they were sharing with this carbon. So that's why when they move, now the positive charge is here because this hydrogen removed or took those two electrons, becoming an hydride, and that hydride was the one that was shifted, okay? So, and the shift once again, 1, 2, okay? From carbon 1, 2. So we have the hydrogen, the hydride shift from carbon 1 to carbon 2. We have here a secondary um, carbocation, and this create a tertiary carbocation. Now let's look this pretty quick. Instead of moving the hydride, if I move the methyl to here, what I will create in here, it will be what type of carbocation if I move this methyl group to this carbocation. It will be a secondary carbocation. So from secondary to secondary, that's not allowed. So that's why I can't do a methyl shift in this reaction, but I can do a hydride shift in a way to create the more stable carbocation, and then the nucleophile attacking the electrophile again to create my product. Okay, so we can have methyl shift and hydride shift following that rule that needs to be 1 and 2 carbons together, okay, the neighbor carbon, and also to create a more stable carbocation. Methyl shifts from quaternary carbons are common as tertiary carbocations are the results. Tertiary carbocations also result via hydride shift from tertiary carbocations that we showed before. Whenever you see a secondary carbocation in a reaction mechanism, be on a lookout for rearrangement possibilities. So whenever you produce a carbocation in a mechanism, always watch out. Maybe you can have a shift of a methyl or a hydride group, and in that way you can have a carbocation rearrangement. Now, what happened then with the methyl and primary alcohol? Because we have been talking about the tertiary and secondary alcohols, okay? And remember, tertiary and secondary always are going to produce carbocation. That's why they go through unimolecular nucleophilic substitution. So now, what happened with the primary? What happened with the methyl group? Can they make this type of reaction with hydrogen halides to create halide alkyls? The answer is yes, okay? But it's going to go through a different mechanism. It can go through the unimolecular nucleophilic substitution because through that mechanism, we're going to create carbocations. And we know that primary and methyl carbocations are pretty unstable. So they can go through Sn1 reaction, okay? So what type of reaction or mechanism they're going to go through? Let's go over this. So how then do methyl and primary alcohols react to form alkyl halides? And they do react, okay? We can have this type of product, but it's not going to be through the SN1 reaction. However, the steps are pretty similar, okay? So as we expected, the first step should be what? This is an acid. This can behave as a what? As a base. So we're going to protonate this. Okay, that's the first step. The protonation and creating that living group, making a better living group. Okay. And then usually in this SN1 mechanism, this living group is released. Okay. And you create the carbocation. In here, due to the possible carbocation that you're going to produce is so unstable, the living groups is going to wait until the nucleophile attack. Okay, so that molecule is going to wait to another molecule to attack, and then when they attack, the living group is going to leave, but they never are going to go through the carbocation. Okay, so once I create a molecule of water, that living group is going to stay there due to is a methyl group or a primary alcohol. Okay, and because of that, they're going to wait for the nucleophile to attack that carbon, and then that living group is going to leave. Okay, and we're going to have our product. So basically, something like this. So we have here the molecule of water that is leaving, but it's waiting for that nucleophile to attack and attach to this side of the molecule. And as you can see here, is attacking in the back face of this one. Okay. So what type of configuration you think is will have theoretically? Is going to be inversion. Okay. And I say theoretically because we know that we don't have a absolute configuration here. So it's not going to affect that. But in theory, that will basically create inversion of configuration all the time. Okay. The slow step is the bimolecular step two. Hence, this mechanism is called bimolecular nucleophilic substitution. So because it takes in account two molecules, this one and this one. So that's what is known by a bimolecular type of mechanism. Bimolecular nucleophilic substitution, SN2 mechanism. So sometimes because we have other functional groups in the molecule, acid conditions are pretty harmful, okay, for that molecule. So we need to look for some kind of mild conditions in a way to obtain our alkyl halogenated. Okay, so as long as we can use some kinds of condition that are going to be mild in a way to prevent that other parts of the molecule can react with acid, we have other ways that we can do that. So alkyl halides are very important synthetic precursors and sometimes interesting in their own right. The stereochemical course of an alcohol and hydrogen halides can be unpredictable, as we saw before, due to the difference and non-symmetric phases of some substrate. Many functional groups are not stable to concentrated hydrochloric acid, so milder conditions are necessary. So we need to find some type of reagent that are going to be mild in a way to produce this halogenation. Okay. So, like alcohols and HX, other methods are based on turning the hydroxyl group into a good living group. So the first one that we're gonna learn today is the thionyl chloride. Okay, the thionyl chloride is SOCl2. This SOCl2, as you may expect, is gonna add a chloride ion or atom to the alcohol. So we're gonna substitute this OH with the chlorine of SOCl2 or thionyl chloride. And we need amine. Amine is basically like a catalyst, okay, in this reaction. So it's important to use an amine whenever we use the thionyl chloride as part of the reaction. If you don't have the amine, the reaction is going to happen, okay? So that's why you have the alcohol, thionyl chloride, triethyl amine, and this product is going to be the alkyl chloride, sulfuric dioxide, and trimethyl ammonium chloride. This reaction is another one that you need to put in your index card, okay? Another way that you can create alkyl halides. And you can just put ROH alcohol. You can put an arrow SOCl2 and the bottom you can write there amine. That's it. You don't have to put triethylamine. Just that with the knowledge that you need an amine, and then the product is going to be the RCl, the alkyl chloride. That's the reaction that you need to learn. Okay. Once again, the alcohols in the presence of thionyl chloride with amine is going to produce the alkyl chloride. Reaction number two that should be in your index card. So this is going to produce an inversion of configuration. And here we have the alcohol. This one is a tertiary type of alcohol, SOCl2 thionyl chloride, triethylamine or amine. And the product of this is going to be the inversion of configuration, okay, of the alkyl halide. So here we have an S absolute configuration. Here's going to be the R. So something like this that you can write in your index card is going to be more than enough. The alcohol, thionyl chloride, triethylamine, and the alkyl halide. The key intermediate is an alkyl chlorosulfide. Okay, this is going to be basically this component here, this compound attached to the oxygen, creating the chlorosulfide. And this is an excellent living group. Okay, this is an excellent living group. The Sn2 displacement by chloride generates the product. So then the chloride in here, that is a nucleophile, is going to attack this carbon in here, which is my electrophile, and there's going to be release, and that's how it's going to attack from the bottom because this is so big that it can attack this same phase. So that's why you have the inversion of configuration. Okay, so it's attacked from the bottom, and the chloride is going to be attached to this carbon from the bottom side. And if you start with the R, you finish with the S. If you start with the S, you finish with the R. Okay, remember, it's through inversion of configuration. Another way to do this type of alkyl halides is using phosphorus trihalide. Okay, this basically is PBr3 or PCl3. Both of them are going to produce alkyl halide. If you need to add a bromine, you can use PBr3. Okay, if you need to add a chlorine, you can add PCl3 with the alcohol. So here we have 3ROH with the PX3, that could be chlorine or bromine, to produce three alkyl halides and the phosphorus acid. Okay, this is the third reaction that you need to put in your index card and you need to learn. Okay, so these are three ways that you can produce the alkyl halide. The first one is the alcohol with the hydrogen halide. The second one is the alcohol with the thionyl chloride and the amine, triethylamine. And the third one is the alcohol with phosphorus trihalides, could be PCl or PCl3 or PBr3, and that's going to give you your alkyl halide. So here we have one example. We have 2-methyl 1-propanol. So we're going to substitute this OH with a bromine, and that's going to be my product, 1-bromo 2-methyl propane. From an alcohol to an alkyl halide. This is another example using also PB3. You can also use PCl if you want to add a chlorine. So we have the secondary alcohol in here. You're going to substitute the OH with the bromine, and that's going to be your product. Now, in this part, we're going to talk a little bit about sulfonates. Now that we talk about the thionyl chloride, we have a type of sulfonate in there, and how they can be used as good living groups. Okay. Sulfonates as pseudo-halides. So remember when we talk about the beginning of this chapter that the importance of why to create alkyl halides is because they are a good intermediate when we want to go from one compound to another one, and it's because that halide is a really good living group. Okay, so if we can substitute that living group to another more efficiently, that will be great. And sulfonates add excellent living groups. Okay, so we've seen that chlorosulfides groups is a good living group, as we saw before. Okay. Halogens themselves are good living groups. That's where their value lies, as I mentioned. So a functional group related to the chlorosulfide called a sulfonate is also a good living group. So the sulfonate is going to be the next one that we're going to see in here. It's going to be this one. Okay, this is sulfonate. So sulfonate have the general structure of ROSO2R. Okay, this one is alkyl, which is this one, methane sulfonate. So sulfonate, methane, and this is the alkyl methane sulfonate. The most common sulfonate are toluene sulfonate. Okay, in this case, we're going to have a toluene in here and methane sulfonates. So we have here the methyl sulfonate. Okay, and instead of a methyl, we can have then the toluene, that is this group in here, the arene group or benzene group with the methyl group attached directly to the sulfur, okay? And this is also the TSCl, this toluene sulfonyl chloride, or the methane sulfonyl chloride. So in a reaction, the sulfonates are made from alcohols using the corresponding sulfonyl chloride and the amine again. So here we're gonna basically, this is a modification of the oxygen. We're trying to make oxygen a better living group, okay? Better than water, okay? So OTS, that is this one, is an awesome living group, okay? Better than water. So that's why we create this one. This still have the same configuration. Okay, we have the S in here, because we haven't done a substitution of the OH. We are just modifying the oxygen from OH to OTS. Okay, so that's why you keep that configuration because we're not working in that carbon. Okay, the reaction is not in the carbon, is in the oxygen of the alcohol. So that's why you have the retention. So with this alcohol and this sulfonyl chloride, you're going to create that sulfonate, which is an excellent living group. Now, any kind of nucleophile can attack this carbon, and that's going to release, and you're going to have your product. Same thing here, okay? So now a nucleophile can come from the backside, and now you will have inversion of configuration, okay? But the addition of this um, TS, okay, the toluene sulfonate, is not going to alter the configuration. It's going to keep the same one because the reaction is not in the carbon. The reaction is in the oxygen of the alcohol to make it a better leaving group. Okay. And with that, we finish our chapter number 5. I hope that you learned something today and it was a little bit fun. So thank you for your attention, and we're going to answer questions the next time we met. Bless one.